Let's talk about gas laws. So here's how you can use this video. During this video, there'll be slides that have text highlighted in green. If you're using this to take a notebook, that's what you should write in your notebook. And throughout the video, there'll also be some blue text. These are questions for you to consider and or practice problems for you to answer. Now, also throughout this video, there's going to be two codes. One will be a written code said by one will be a written code that'll show up on the screen, and one will be a verbal code said by myself at any point in the video. That can happen in any order, so pay attention. So let's get started. So we're talking about gas laws. Let's talk about what a gas is, right? A gas has no definite shape, so it's not rigid, no definite volume, and does take the shape of the container. It is the least dense state of matter. So they expand to fill a container. They're able to be compressed. So because of this, we need to look at the laws, because you can change the volume of gases, and they're going to behave differently, right? Yeah, and gas particles, they bump into each other, and they bump into the sides, and that's what is going to cause like the pressure. Now, a vapor is a substance that is a gas, but it's usually a liquid or a solid at normal room temperature. So an example would be like water vapor, right? But it is a gas, right? So this is how gases behave. So the gas laws describe how gases behave by examining the relationship among the four fundamental variables: pressure, volume, temperature, and moles, right? So when one of them changes, the others can change in a predictable manner based on these laws. They're constantly moving, altering their conditions, changing how often and how forcefully they collide into each other. So let's just talk about these four conditions of gases. So temperature is the measure of the average kinetic energy of gas particles. Now, for these definitions, I'm going to give them to you in terms of gases, right? So yes, temperature is just the average kinetic energy of any like molecules or atoms, but for our gas laws, it's the kinetic energy of those gas particles. Now, gas laws equations require Kelvin be used, right? So that is one of the temperature units that we can use, right? And that's because 0 degrees Kelvin is the point at which no motion happens, right? There's no molecular motion. So you can look at these. These are probably the two that most of you are going to be familiar with. Fahrenheit, that's what most Americans are familiar with. Celsius is what the rest of the world uses, and the scientific community does use this one, right? So Celsius, 0 degrees Celsius is freezing point of water. 100 degrees Celsius is the boiling point of water. Now, Kelvin is very similar to Celsius. In fact, the spacing between those two temperature measurements are the same, right? So if you go up 1 degree Celsius, it does go up 1 degree Kelvin, or the same. Or it's not even it's 1 Kelvin. It's not even degrees Kelvin, because it's an absolute value, which means we measure it from an absolute point. The starting point is 0 degrees Kelvin. That's the point when all motion stops. In order to get there, to calculate from Kelvin to Celsius, it's Celsius plus 273.15, right? So that's how you can convert. We need our measurements to be in Kelvin, because our variables require, our laws require us to not have a negative temperature. So you can see here there are these thermometers. I like it shows the motion. Like all particles are moving. When we're talking about gases, right? They're moving. They're really energetic, and the average kinetic energy, that is the temperature. Now, pressure is the force of gas particles colliding with the walls of their container. So pressure can be measured in atmospheres, millimeters of mercury, torr, kilopascals. And one that I left off there is PSI. It's probably one that most people are familiar with, like with the tires, right? Pounds per square inch. That is a pressure, right? Now, for these videos and like any calculations, I'm going to use atmospheres, ATM, right? So 1 atmosphere is like an atmosphere here at sea level. But you can use really any of the other you can use any of the other pressures, right? The equations would still work out. It's just that there is one, you need to change the constant in one of the one of the equations. But if you take a look at this little graphic over here, you can see here, these are the gas particles. They're moving around. Notice they're bouncing off each other. They're bouncing off the walls. If you were to like count all the collisions with the walls, that force is providing an outward pressure. So more pressure means more collisions with the walls, more force moving outwards. That's why, like, if you have a tire, like, think of this as a tire. I know it's square, but think of it as a tire. The pressure is the force of all these particles bumping outward. You have more. If you add more particles, or even heat it up, that's going to increase the pressure. It's going to increase the number of collisions, the pressure on that. The next one is volume, right? So volume describes the amount of space a gas occupies. Now, volume can be measured in many units, right? But for gas laws, we're going to use liters. Gas is affected by changes in pressure, temperature, and the number of moles of gas. Changing the container size or conditions will change the space available to the gas particle. So one thing, like, the other variable is affected, but basically it's the container or whatever's holding that gas. The gas is going to fill that container, like we've learned in the definition, and that's going to be the volume, right? It's going to fill the shape of that container. That is going to be the volume of the gas. And moles is the last one. Now, moles is just the measure of the amount of gas in terms of the number of particles, right? So a mole is just a number. It's like a dozen, except it's 6.022 times 10 to the 23rd. It's a lot, right? And the reason why we do this is because it's a way to count particles based on their mass, or in terms of gases, their volume, right? We know exactly how many particles are in there, right? More moles means more particles to collide with the container. That can change the pressure and the volume. Now, gas law's equation uses moles to relate the quantity of gas to how it behaves. So adding or removing gas will change a system's pressure, volume, or both, right? And we'll get to this, right? So these are the four conditions of gas, or the four variables, or properties of gas. Now let's take a look at how they affect each other, right? So here's a question, right? How does pressure affect scuba divers? So let's take a look at Boyle's law to answer this one, right? So Boyle's law, and here's the equation, right? Now it can also be written as P times V equals like a constant, but these laws, the three laws that we're going to learn right now, these are good at saying, okay, great, I've got this condition and this changes, then I can calculate the other ones. So Boyle's law states that when temperature and moles are constant, pressure and volume are inversely related. So inverse means opposite, right? One goes up, the other goes down. One goes down, the other goes up, right? That's what inverse means. And this law shows how gases compress and expand in predictable ways. So a real-world example is how syringes work, right? Pushing the plunger decreases that volume, causing pressure inside to rise, and it forces the liquid out. So you can see over here, this is like, think of this as like a plunger. Well, you're decreasing the volume, thus increasing the pressure inside, right? So they're inverse. One goes down, the other goes up. One goes up, the other goes down, right? And this has a lot. This is what affects scuba divers, right? Because if you're at a lower, if you're at a lower depth, like that pressure on you is greater. It's a greater pressure, so lower volume. But as you go up, well, what that's going to do is it's going to decrease the pressure and increase the volume. That's why, like, the number one rule of scuba diving is never hold your breath, because, well, if you're going up or down, that's going to change the volume inside your lungs, especially if you're going up. Decreasing the pressure will increase the volume. It can actually cause damage to your lungs. So that's how it affects scuba divers. But this also, like, is why, like, if you're on an airplane or you're going up a mountain, that's why your ears pop, right? Because your body, the sinus cavities, that's the place that has air. When you change the pressure, that difference in pressure is going to cause, like, your ears to pop. That's it, equalizing the pressure, right? So it does really have it. Yeah, it has to do with, like, volume. It's like pushing it out as well, but it's like mostly equalizing it, right? So that's Boyle's law. Now, Charles' law, or I believe this is French. I've heard it like Charlet's law, but, well, I'll just call it Charles' law. But Charles' law, and this is the equation, it states that when pressure and moles are constant, volume and temperature are directly related, right? So that means one goes up, the other goes up. One goes down, the other goes down. And as temperature increases, gas particles move faster and spread farther apart, increasing the volume. So hot air balloons work this way, right? Now there's more going on with the hot air balloon, but like what you're doing is you're heating it up, and you can see over here, this is a balloon, but like, a balloon in a candle. You're heating of those particles. Well, the volume is going to expand, right? If it's able to expand, it's going to expand. All right, or it's going to go the other way. If you cool it down, it will contract. So that's Charles' law, right? It describes volume and temperature directly related. Means one goes up, other goes up, one goes down, the other goes down as well, right? Directly related. And the last one is Gay-Lussac's law, right? So Gay-Lussac's law, and here it is, right? Here's the equation that states that when volume and moles are constant, pressure and temperature are directly related. So once again, another direct relationship. One goes up, the other goes up. One goes down, the other goes down. As temperature rises, gas particles move faster and collide harder and more often, increasing the pressure. So this is would be like a rigid container. So here's an example, right? So the pressure inside like an aerosol can increase when heated, which is why they warn not to leave the cans in like hot cars, right? So think about like a rigid can, right? So here's an example, this little graphic over here. So you can see here, well, you heat it up, well, those particles are going to start moving faster. They're colliding with the walls. It's more and more pressure. But if I cool it down, they're moving slower, less collisions, less energy, less pressure, right? So that's Gay-Lussac's law. These laws just describe how they interact, or how if I change one, how the others are changed. Now, let's put them all together. In order to do that, we need to have a starting point, and that's standard temperature and pressure, or STP, right? It provides a reference point when comparing gas measurements, right? So for the other ones, it was just, hey, we're looking at these two variables, something changes, how does the other one change? Great. Well, now we're going to put it all together. Now, STP is defined as 100 kilopascals, or that's about 1 atmosphere, right? So I've seen it both ways. They're not exactly, right? It's not a one. It's not a one. I think 1 atmosphere is like 101 something kilopascals. But I've seen it written both ways. I think that the official one right now is 100 kilopascals, but I think in the past it's been 1 atmospheres. You might see them both ways, but like officially right now, it's 100 kilopascals of pressure at 273.15 Kelvin, or 0 degrees Celsius, right? So at STP, at this pressure and temperature, 1 mole of any gas occupies 22.4 liters. So this gives us a starting point for all 4 of the properties of the gas, right? So it allows us to compare gases consistently, right? So it doesn't matter. And I like this little graphic here, right? So I'll put this over here. The little graphic here is saying, okay, great. I've got these different gases, and I've got them at a bunch of different temperatures. But notice what happens when the temperature is made the same and I've got the same pressure. So at 1 atmosphere, or 100 kilopascals, right? At 0 degrees Celsius, all gases are going to be the same. It doesn't matter whether it's nitrogen, oxygen, hydrogen, chlorine, helium, any gases, right? It's going to be the same, right? So that gives us a starting point, which brings us to our big equation. At this time, I'll go ahead and give you that verbal code is 687. I say that again, the verbal code is 687. Now that brings us to the ideal gas law, right? So here's the ideal gas law. PV equals nRT, right? It combines all the individual gas laws into a single equation, right? So this equation relates pressure, volume, temperature, and moles to describe gas behaviors under many different conditions. It basically takes all of the ones that we've learned, Boyle's law, Charles' law, Gay-Lussac's law, puts it into one equation that is the ideal gas law, right? Now here's the thing, you're probably looking at that and saying, well, I see pressure, I see volume, N is the number of moles, T is temperature. Now, R is the gas constant, right? It basically ensures the units match. And this is not going to change with any problem, right? Like any problem, any pressure, volume, number of moles, or temperature. The only reason why it would be a different number is depending on what pressure unit is being used. So for atmospheres, R is going to be 0.0821. And you can see the unit, liter atmospheres per mole Kelvin. That just ensures all the units line up and I'm behaving that. So other pressure values are going to have different uh, uh, are going to have different constants there, right? But that puts it all together, right? So this is almost like almost every single gas law change is going to have this. A real good examples of like airbags, right? So when airbags go off, the ideal gas law, right? So chemical reactions, well, it's going to produce a gas rapidly, right? Changes the numbers, right? That's going to increase the moles, the temperature, and it inflates. It changes the volume. A lot of stuff is happening when airbags go off, right? But I just want you to see here. This is just for good. This is kind of hard to explain because if you change one of them, like we saw in those other three laws, that does affect other ones. But the other laws describe, hey, if I've got these as constant, but it's not that simple. This is really good at saying, hey, under these conditions, how does this gas behave for this one, right? The other laws help us decide, well, if I change this, what's going to happen to the other variables? So that's the ideal gas law. So just as a final thought, remember there's too much unknown in the universe to take a break from learning. Get out there and question everything.